Another day, another story. The question of whether Mars ever supported life has captivated the imagination of scientists and the public for decades. Central to the discovery is gaining insight into the past climate of Earth's neighbor. Was the planet warm and wet, with seas and rivers much like those found on our own planet? Or was it frigid and icy, and therefore potentially less prone to supporting life as we know it? A new study finds evidence to support the latter by identifying similarities between soils found on Mars and those of Canada's Newfoundland, a cold subarctic climate. Welcome to Tabo Eminent channel. The study, published in Communications Earth and Environment, looked for soils on Earth with comparable materials to those of Mars's Gale crater. Scientists often use soil to depict environmental history, as the minerals present can tell the story of landscape evolution through time. Understanding more about how these materials formed could help answer long-standing questions about historical conditions on the red planet. The soils and rocks of Gale crater provide a record of Mars' climate between 3 and 4 billion years ago, during a time of relatively abundant water on the planet, and the same time period that saw life first appear on Earth. Gale crater is a paleo-lake bed. There was obviously water present. But what were the environmental conditions when the water was there? Says Anthony Feldman, a soil scientist and geomorphologist now at DRI. We're never going to find a direct analog to the Martian surface because conditions are so different between Mars and Earth. But we can look at trends under terrestrial conditions and use those to try to extrapolate to Martian questions. NASA's Curiosity rover has been investigating Gale crater since 2011 and has found a plethora of soil materials known as X-ray amorphous material. These components of the soil lack the typical repeating atomic structure that defines minerals, and therefore can't be easily characterized using traditional techniques like X-ray diffraction. When X-rays are shot at crystalline materials like a diamond, for example, the X-rays scatter at characteristic angles based on the mineral's internal structure. However, X-ray amorphous material does not produce these characteristic fingerprints. This X-ray diffraction method was used by the Curiosity rover to demonstrate that X-ray amorphous material comprised between 15 and 73% of the soil and rock samples tested in Gale crater. You can think of X-ray amorphous materials like jello, Feldman says. It's this soup of different elements and chemicals that just slide past each other. The Curiosity rover also conducted chemical analyses on the soil and rock samples, finding that the amorphous material was rich in iron and silica but deficient in aluminum. Beyond the limited chemical information, scientists don't yet understand what the amorphous material is, or what its presence implies about Mars's historical environment. Uncovering more information about how these enigmatic materials form and persist on Earth could help answer persistent questions about the red planet. Feldman and his colleagues visited 3 locations in search of similar X-ray amorphous material: the tablelands of Grosmorne National Park in Newfoundland, Northern California's Klamath Mountains, and western Nevada. These 3 sites had serpentine soils that the researchers expected to be chemically similar to the X-ray amorphous material at Gale crater, rich in iron and silicon but lacking in aluminum. The 3 locations also provided a range of rainfall, snowfall, and temperature that could help provide insight into the type of environmental conditions that produce amorphous material and encourage its preservation. The study site in the tablelands of Newfoundland. Credit: Anthony Feldman/DRI. At each site, the research team examined the soils using X-ray diffraction analysis and transmission electron microscopy, which allowed them to see the soil materials at a more detailed level. The subarctic conditions of Newfoundland produced materials chemically similar to those found in Gale crater that also lacked in crystalline structure. The soils produced in warmer climates like California and Nevada did not. This shows that you need the water there in order to form these materials, Feldman says. But it needs to be cold, near freezing mean annual temperature conditions in order to preserve the amorphous material in the soils. Amorphous material is often considered to be relatively unstable, meaning that at an atomic level, the atoms haven't yet organized into their final, more crystalline forms. There's something going on in the kinetics, or the rate of reaction, that is slowing it down so that these materials can be preserved over geologic time scales, Feldman says. What we're suggesting is that very cold, close to freezing conditions, is one particular kinetic limiting factor that allows for these materials to form and be preserved. This study improves our understanding of the climate of Mars, Feldman adds. The results suggest that the abundance of this material in Gale crater is consistent with subarctic conditions, similar to what we would see in, for instance, Iceland. Discoveries suggest that Mars had a cold and icy past, rather than the warm and wet environment that was once widely believed. Evidence supporting this theory includes ancient glacial features, satellite images and data from Mars rovers have revealed landforms resembling those created by glaciers on Earth. These features include valleys, moraines, and other geological structures that indicate the movement of ice across the Martian surface. Climate models, computer simulations of Mars' ancient climate suggest that the planet was too cold to support long-term liquid water. Instead, any water present would have likely existed as ice, potentially melting briefly due to volcanic activity or meteor impacts. Geological evidence. Glacial landforms, high-resolution images from satellites like the Mars Reconnaissance Orbiter, MRO, have revealed features reminiscent of glacial landscapes on Earth. These include valley networks, previously thought to be carved by flowing rivers. Many Martian valleys show characteristics more consistent with glacial activity. These valleys often have U-shaped cross-sections, similar to those formed by glaciers on Earth. Moraines, accumulations of debris at the edges of former glaciers, have been identified in several locations on Mars. Eskers, long, winding ridges formed by streams flowing under glaciers, have been found on Mars, further supporting the presence of ancient ice sheets. Climate models and simulations. Cold climate models, advanced climate models simulating Mars' ancient atmosphere and surface conditions, suggest that the planet's temperature was generally below the freezing point of water. These models take into account factors such as solar radiation. Mars receives less sunlight than Earth due to its greater distance from the Sun, contributing to a colder climate. Atmospheric composition. Mars' thin atmosphere, primarily composed of carbon dioxide, lacks the greenhouse effect necessary to maintain warm surface temperatures. Volcanic activity. While volcanic eruptions could have temporarily warmed the planet and caused localized melting of ice, these events were likely sporadic and insufficient to create a stable warm environment. Mineral and sediment analysis. Cold-formed minerals, rover missions, such as those conducted by Curiosity and Perseverance, have analyzed Martian rocks and soils, finding minerals indicative of cold climate formation. The cold and icy past of Mars paints a complex picture of the planet's history, offering both challenges and opportunities for understanding its potential to support life. Thanks for watching. Request you to subscribe the channel.